Today, my topic is neutron-proton scattering below 10 MeV or partial wave analysis of the neutron-proton scattering at low energy, assuming a central potential with square well shape. As I have already discussed in my previous videos, that to determine the characteristics of nuclear force, there are two methods. One in which we study the bound system of nuclei, and is to study the nuclear-nucleon scattering. In nuclear-nucleon scattering, we can study neutron-proton scattering, proton-proton scattering, and neutron-proton scattering. Again, in all these three cases can be divided into two categories: low energy scattering and high energy scattering. So in this topic, I will discuss neutron-proton scattering at low energy, that is below 10 MeV. And there is a reason why I have categorized it or named it neutron-proton scattering below 10 MeV, that I will discuss later on. I have divided this topic into different subtopics. So let me start part A of this topic. As we know that the information about the internucleon forces, that is nuclear force, can be obtained from a study of the scattering of free neutrons by protons. In such experiments, a parallel beam of neutrons is allowed to impinge upon a target containing hydrogen atoms, and the number of neutrons deflected through various angles is determined as a function of neutron energies. These scattered neutrons from the protons are detected by detector at different angles. Since neutrons have no charge, they are unaffected by the electrostatic field, and therefore the scattering of neutrons by the protons will directly reflect the operation of the nuclear force. Means we will get information from this scattering only about nuclear forces between neutron and proton. The kinds of reaction can be involved in NP scattering: one scattering and other radiative capture. It means when a target nuclei is bombarded by a beam of neutrons, then there are two possibilities. Certain neutrons will be scattered and remaining neutrons will be captured by the target nuclei. That is known as radiative capture. The latter has low probability and cross-section for high energy neutrons, as the cross-section for the competing radiative capture reaction decreases with 1 upon v, where v is the neutron velocity. The scattering of neutron on proton depends considerably on the energy of the neutrons. Why I have categorized this topic below 10 MeV or the scattering below 10 MeV? Because the de Broglie wavelength in center of mass system is long compared to the range of the nuclear forces. Therefore, neutrons of orbital angular momentum larger than 0 do not come close enough to the proton to be appreciably scattered. इसका मतलब ये है कि जो भी न्यूट्रॉन्स जिनका एंगुलर मोमेंटम वैल्यू L 0 से ज़्यादा है, यानी 1, 2, 3, 4 और उससे भी ज़्यादा है, वो प्रोटॉन्स के इतना क्लोज नहीं आ पाते हैं कि उनके बीच किसी भी तरह का फोर्स या इंटरेक्शन हो सके. So the scattering is due only to the L equal to 0 neutrons, and also it is isotropic in the angle. It means all the neutrons which are scattered, basically they are scattered equally in all directions in center of mass system. Now the chemical binding energy of the proton in a molecule is about 0.1 electron volt. Thus, for neutron energy greater than 1 electron volt, the proton can be assumed as free. इसका मतलब ये है कि अगर एक न्यूट्रॉन जिसकी एनर्जी 0.1 इलेक्ट्रॉन वोल्ट से ज़्यादा है और वो जब किसी ऐसे टारगेट पर बम्बार्ड किया जाता है जिसमें प्रोटॉन्स हैं, तो वहाँ प्रोटॉन्स को हम फ्री प्रोटॉन्स ट्रीट कर सकते हैं। ऐसे मॉलिक्यूल्स में जो प्रोटॉन्स हैं, जैसे हाइड्रोजन गैस में जो हाइड्रोजन मॉलिक्यूल्स हैं, वो हाइड्रोजन मॉलिक्यूल्स हाइड्रोजन एटम से बने हैं और हम जानते हैं कि हर हाइड्रोजन एटम में एक प्रोटॉन होता है। सो दीज प्रोटॉन्स कैन बी ट्रीटेड एज फ्री because they will get enough energy so that they can be treated as free. This sets a lower limit to the neutron energy. Means जब हम ये एक्सपेरिमेंट परफॉर्म करते हैं तो न्यूट्रॉन की एनर्जी 1 इलेक्ट्रॉन वोल्ट से ज़्यादा होनी चाहिए और 10 मेगा इलेक्ट्रॉन वोल्ट से कम होनी चाहिए, क्योंकि उसी केस में हम ये मान सकते हैं कि जो स्कैटरिंग हो रही है वो L इक्वल टू ज़ीरो, अर्थात ऑर्बिटल एंगुलर मोमेंटम वैल्यू न्यूट्रॉन्स की वही स्कैटर्ड होते हैं जिनकी वैल्यू ज़ीरो है। ज़ीरो से ज़्यादा वाले मैग्नेटिक एंगुलर मोमेंटम वाले जो न्यूट्रॉन्स हैं उनकी स्कैटरिंग इनसिग्निफिकेंट होती है। Now we shall treat this NP scattering as if it were purely elastic, because this is not quite correct. Although this is not quite correct. Also, we assume here that radiative capture is negligible for neutron energy above 0.1 electron volt. Now, watch this diagram. There is a plane incident beam of neutrons shown by arrows, number of arrows, and this beam is represented by e raised to power I k z, and there is a circle which represents the target nuclei, means proton in this case, which is placed, we can assume that it is placed at the origin O. Now let us discuss part B of this topic, that is scattering cross section or phase shift analysis of neutron-proton scattering. The quantum mechanical problem dealing with the collision in the center of mass system between two particles of mass m is equivalent to the problem of a collision between a particle of mass m by 2 and a fixed scattering center. So, because of certain reasons, we will treat this problem in a center of mass system. In center of mass system, the Schrodinger equation for the two-body problem, that is neutron-proton system, can be written as del square psi plus m upon h cross square multiplied by E minus Vr multiplied by psi equal to 0. This is equation number 1. Here m is the proton or neutron mass, which will be equal to 2 into reduced mass. Here E is the incident kinetic energy of neutron in center of mass system, and V, which is basically a function of R. R means the distance between the neutron and the proton, and this will be equal to internucleon potential energy. Psi is a solution of Schrodinger equation 1. We know that psi describes a beam of incident particles plus a scattered wave of particles going away from the scattering center. Scattering center means a proton in this case. And this can be written as psi equal to psi incident plus psi scattered, because we know that the total wave function must represent a certain part of incident wave and remaining part of scattered wave. At large distances from the center of scattering, the solution of equation 1 is expected to be of the following form. Psi is equal to e raised to power I k z plus e raised to power I k r upon r multiplied by f theta. And since we are treating this at a large distance from the scattering center, so this equation is for r tends to infinity. Here psi incident is equal to e raised to power I k z, as I told you earlier. This represents a plane wave moving in z direction towards origin. That is, this equation describes a beam of particles that is undisturbed by the scattering center. ये e raised to power I k z इक्वल टू साइन इंसिडेंट, ये वेव के उस पार्ट को रिप्रेजेंट कर रहा है जो इंसिडेंट हो रही है, और चूंकि वो इंसिडेंट हो रही है तो इसलिए अभी तक वो स्कैटरिंग सेंटर से अनअफेक्टेड है, यानी उनके बीच अभी उस बीम और स्कैटरिंग सेंटर के बीच अभी तक कोई इंटरेक्शन नहीं हुआ है. Psi Sc is equal to e raised to power I k r upon r multiplied by f theta represents the scattered wave, and f theta is equal to amplitude of the scattered wave in the direction theta with respect to the incident beam. Here k is equal to under root me upon h cross square, where m is the mass of either neutron or proton. The wave function psi incident represents one particle per unit volume, since the square of the wave function is equal to the unity. The incident flux is v particles per unit area per second, where v is a particle velocity. These issues I have already discussed in my previous video. Now let us first consider the wave equation 1 in the absence of scattering center. And in the absence of scattering center, we can consider Vr is equal to 0, because if scattering center is not there, there will be no interaction between the neutrons and proton. So we can assume Vr is equal to 0. Now in that case, above equation becomes del square psi plus me upon h cross square multiplied by psi is equal to 0. Now equation 4 will have the solution psi incident is equal to e raised to power I k z, because we know that above equation shows only the undisturbed wave, and that is represented by psi incident is equal to e raised to power I k z. This wave function can be expanded into a series in terms of spherical harmonic functions, as written below. You can observe, and this is given by equation 6. Here L, that is orbital angular momentum, is the integer representing the number of partial waves. Basically, the scattered wave will consist of number of partial waves corresponding to different L values, corresponding to different angular momentum values. The radial functions RLR are the solutions of the radial part of equation 4 and can be represented in terms of spherical Bessel functions, as shown by equation 7. So after certain calculations, as you can observe here, PL cos theta is the Lagrange polynomials of order L. We will get equation 10. Now for incident neutrons, for kinetic energy less than 10 MeV in the laboratory system, the only partial wave involved in the scattering is the L equal to 0 or S wave, as we have already discussed initially. Equation 6 can be expressed now as psi is equal to R0R Y00 theta plus summation from L equal to 1 to infinity RLR YL0R. So here we are using 0, R0, Y0, because we are using only the partial wave corresponding to L is equal to 0. Now putting the values, rather using the equations 7 and 9, we can write psi is equal to sin kr upon kr plus e raised to power I k z minus sin kr upon kr. The first term corresponds to the spherically symmetric partial wave, that is S wave. For S wave scattering, only the first term is affected and can therefore be written as psi s in the presence of scattering potential Vr. So we can write it as psi s is equal to ur upon r. When the interaction in the form of scattering potential in the neighborhood of the origin is turned on, nothing can happen to the incoming part of the wave function at distances larger than the range of the nuclear force. अब इस पार्ट में अब तक हमने ये माना कि जैसे स्कैटरिंग सेंटर है ही नहीं। अब मान लीजिए स्कैटरिंग सेंटर रखा हुआ है, तो इसका मतलब ये हुआ कि जो न्यूट्रॉन बीम है उसमें जो न्यूट्रॉन्स हैं वो उस स्कैटरिंग सेंटर से स्कैटर्ड होंगे। और चूंकि हमने ये माना है कि एब्जॉर्शन ऑलमोस्ट निल है, इसका मतलब ये हुआ कि जितने भी न्यूट्रॉन्स इंसिडेंट हो रहे हैं वो सारे के सारे स्कैटर्ड होंगे। अर्थात स्कैटर्ड बीम की जो इंटेंसिटी है उस पर कोई भी फ़र्क नहीं पड़ेगा, उसके एम्पलीट्यूड अर्थात इंटेंसिटी पर कोई फ़र्क नहीं पड़ेगा। तो फिर क्या चेंज आएगा स्कैटर्ड बीम में? स्कैटर्ड बीम में जो चेंज आएगा वो आएगा फेज़ का। द फेज़ ऑफ द स्कैटर्ड बीम विल चेंज विद रेस्पेक्ट टू और रिलेटिव टू द इंसिडेंट बीम। एंड टू इंक्लूड दिस एस्पेक्ट, as r tends to infinity, the solution ur assumes the form c sine kr plus delta 0, where c is an arbitrary constant and delta 0 is some phase angle. Thus, the complete wave function outside the scattering potential can be written as psi is equal to c sine kr plus delta 0 upon r plus e raised to power I k z minus sine kr upon r. Now, by putting the values of sine in terms of exponentials, we can solve this equation. So in the last part of the equation, the term e raised to power minus ikr represents an incoming spherical wave which is moving towards the origin. Origin means where our proton is situated or scattering center is situated. And e raised to power plus ikr represents an outgoing spherical wave. The above scattered wave, as shown by the above equation, must contain no incoming wave. Therefore, we can write the coefficient of e raised to power minus ikr as 0. So, by putting e raised to power minus ikr as 0, we will have c into e raised to power minus I delta 0 minus 1 upon k is equal to 0. And when we solve this equation for c, we will get c is equal to 1 upon k e raised to power I delta 0. Hence, psi will be equal to e raised to power I k z plus e raised to power I k r upon r multiplied by e raised to power 2 I delta 0 minus 1 upon 2 iota k. This is equation number 12. Now, by comparing this equation 12 with the our standard solution of equation 3, we will have f theta, और इसको सॉल्व करने के बाद हमें इसकी वैल्यू मिलेगी e raised to power I delta 0 upon k multiplied by sin delta 0. And if we take the modulus of the square of this value, then we will get sin square delta 0 upon k square. Since we know that the total scattering cross section will be equal to the integral sigma theta multiplied by d omega, or equal to integral d sigma theta. So, and this will be equal to integral modulus of f theta square multiplied by d theta. Now, by putting the value of modulus of f theta square in this equation, we will get sigma sc is equal to 4 pi sin square delta 0 upon k square, or 4 pi lambda cross square sin square delta 0. This is equation number 14. The analysis here is carried through only for L equal to 0 scattering. Higher orbital angular momentum waves also have to be considered at higher energies. The total cross section can be written as a sum of partial cross section if we consider at higher energy that all the scattering waves consisting of all the partial waves corresponding to different orbital angular momenta, then the above equation becomes sigma L equal to 4 pi lambda cross square multiplied by 2l plus 1 multiplied by sine square delta l. If we know that differential scattering cross section d sigma is equal to d omega sine square delta 0 upon k square. That is, the differential scattering cross section for L equal to 0 neutrons is independent of angle, because there is no theta here. So we can say that differential scattering cross section for L equal to 0 neutrons is independent of scattering angle, that is spherically symmetric in the center of mass system, a fact that has been verified experimentally at low energy. तो इस इक्वेशन से हम ये भी बता सकते हैं कि न्यूट्रॉन प्रोटॉन स्कैटरिंग जो कि लो एनर्जी पर हम कंसिडर कर रहे हैं वो बेसिकली आइसोट्रोपिक होती है, क्योंकि जो न्यूट्रॉन्स स्कैटर्ड होते हैं प्रोटॉन से वो सभी डायरेक्शंस में इक्वली होते हैं। इसको हम कहते हैं आइसोट्रोपिक स्कैटरिंग। थैंक यू।